Okay, so in this video we are going to look at sets, and we'll look at how they are named, what are conventions for noting them, what are the conventions for describing them, representing them, and all such things. So what is a set? Set is, they say so that set is a collection of objects. Set is a collection of objects. Now, collection, it needs to be well defined. It means there should not be anything vague about these objects, about this collection. There should not be anything vague about the collection. And at the same time, we also say that it's a collection of distinct objects. So you cannot put two objects which are undistinguishable from each other in one set. If they are exactly same, then you need to just include them once. You don't need to include them more than once. Now, how do you define sets? Sets are basically defined in a, when you want to represent them, you normally represent them in curly braces. So you have braces here, and if you want to describe a set, then I could say that this is a set of numbers 1, 2, 3, and 4. Normally capital letters are used to describe sets. So this is the set A, and then I might also have set B, which is, sorry, need curly brace here. So we get this 4, 5, 6, 7, 8. Yep. And whenever an element or an object from this collection is a member of a particular set, then we use a symbol like this. So I'll use this here. I'll say 1 is a member of A. So how do you read this? You read this as 1 is a member of A, or 1 belongs to A, or 1 is an element of set A, 1 is a member of set A. Likewise, here I can say that 5 is a member of B, or 5 belongs to B, or 5 is a member of set B. Yeah? You can list more than 2 objects as well. So I can say that 1, 2 are member of A, set A. Yeah, and if an object does not belong to a set, then we just cross it, and then we read it accordingly. So for example, I will say 5 is not a member of set A, or 5 does not belong to A. And likewise here I'll say 9 is not a member of B, or 9 is not a member of set B, or 9 does not belong to B. Okay, there are 2 ways sets are described or sets are represented. First method that we have used here is called roster method. Now in the roster method, you just make a list of the objects that are in the particular set. So here in both A and B, both have been represented, or both have been described in using roster method. Now you can also describe them using method called Setbuilder method. In Setbuilder method, you normally write or prescribe a rule or an algorithm which builds up the list. Yeah, so all the objects that are in the set should follow some particular rule, and that rule can be used to make the set. In fact, this is quite logical and natural, because when you are trying to make a collection, you want the collection, all the items in the collection, to have some distinct property which basically connects them. Yeah, they have to have something common, and that's how you make the collection. And that something common is normally we write as a rule in set building. So I can write these 2 sets A and B here using Setbuilder method. So A, I'll say that A is a set of X, or all x's where such that this symbol here we say such that 1 is less than equal to x less than equal to 4. Now many of you would like to close this, put this curly braces here, and you would believe that this definition is enough for building the set A. But we'll look at it later as to why this is not complete. And likewise B as well. We can say B consists of x such that 4 is less than equal to x, which is less than equal to 8. Yeah? When we do that, I think instead of waiting for clarifying it later, I think we can do it now. But here also we need to tell that x is a natural number. Here also the same thing. You put a comma and you say that x is a natural number. Now that definition is complete. So these two form the set builder method. Okay, let's look at some exercises to work through. So let's take a look at this exercise 1 here. Okay, here we need to write these in set builder form. So I would suggest that you pause the video here for a moment and write these sets in set builder method, and this what you have is basically the roster method. Pause the video for a moment and you try them out on your hand. Okay, I'll write them in set builder method. I'll say that it consists of x such that x is less than equal to 1 less than equals to 5, and x is a natural number. Or there's no one way of describing a set in the set builder method. You can write it in many different ways. So for example, I could write like this as well, and it still is a valid representation of this set. X is a natural number. So this one here, I see that this is all a set of odd numbers. So again, I can say that set x, and x is such that x is equals to 2n minus 1, where, and here I can string as many conditions as I want, separated by commas. So I'm saying that x is 2n minus 1. So my n has some limitations now. I cannot have as many values of n as I want. I just need to cover all these values given here. So I will say n is greater than equal to 1 and less than equals to 6. And then again, I need to also say that, okay, I think I'll clean this thing up, and I need to also say that n is a natural number. That's my set. Later on we'll look as to how to make it even more compact. So that would work. Or you could also write x, that x is between 0 and 12 and x is an odd number. That also is a valid representation of this set. If we look at this one, I can say that it's a set of x values such that all x is such that x is equals to n cube, and then I need to say that n is between 1 and 3, and then I also need to say that n is a natural number. I think I should take a moment here to tell you about at least one set of numbers that we normally use, and that set is n. So n is a set of natural numbers. We'll look at other sets as well. Set of natural numbers, and natural numbers are nothing but 1, 2, 3, 4, and so on. Yeah. Once we know this definition, we can, all these examples that we have done, we can make them compact. So here I'm saying x is a natural number. I just need to say that x belongs to n, and there you go. Again, x belongs to n. Likewise, this makes things compact. N belongs to n. X is an odd number. You can just need to say that, but you already wrote that. X is an odd number. X is X is an odd number. This was already okay. Odd number, and n is a natural number here as well. So I'll just write n is a natural number. There are other ways as well, so I will want you to just stick to this. So natural numbers more than 10, I think you should be able to do that. I'll leave that for you. This 2, 4, 6, 8, and 10, I want you to, I'll just do that as well. Okay, I'll need to do both of these because there's a slight difference in there. So I'll say x such that x equals to 2n, where n is less than equal to 5, and n is a member of set of natural numbers. There's not much difference here. X equals to 2n. This now has infinite number of members. So here all I need to say is 1 is less than equal to. So basically it covers everything. Or 1 less than equal to n, that is included in the definition of n. So you don't need to mention that, because when you say n is a natural number, it means that n is a number starting from 1. N could be any number starting from 1, 2, 3, and so on. Okay, that part done. Let's look at, let's move on to the next thing, which is standard set. That's what I was talking about. So these are the standard sets that we have. N is a set of natural numbers, and these sets are really popular in maths. This is set of integers, so we know what it is. And set of rational number is a set, I mean, here we can use the set builder form to write about this number. So this is a consists of x such that x equals to a over b, and a, b are members of z. So a and b are integers. That's what makes it a rational number. So this is the set of all rational numbers which can be represented in the form a over b. Real numbers are all numbers. Basically, real numbers are set of rational numbers plus the irrational numbers. Irrational numbers are the numbers which cannot be represented in the form a over b, cannot be represented as a fraction. Most popular irrational number is pi. And then another one is e, which is 2 point exponent. E is equals to 2.718281, I think. And this kind of golden ratio is also a irrational number. So they all fall in the real number. Basically, real number contains all the numbers. It contains natural numbers, set of integers, set of rational numbers, and everything. So how would you express set of real numbers as a in the set builder form? I'll leave that to you to do some research. And complex numbers is a set of complex numbers. You know, I'll leave that for you to research and find out how to write that as a. I think we can write that. So set of complex numbers is x, consists of x. X is such that x is equals to a plus b iota, where a comma b belongs to R. So that basically is a set of complex numbers. Just remember that a natural number like 1 is a complex number as well, because 1 is nothing but 1 plus 0 iota, where this is a real number and that is also a real number. So this is a complex number as well. Likewise, integers, or all integers are complex numbers as well. For example, you got -2, you can write that as -2 plus 0 iota. That makes it a complex number as well. And likewise for real numbers as well. So basically you can very well write that natural number is a, oh, we did not talk about subsets, so let's do that first. Subset is, what's a subset? When all the members, all the elements of a set are contained in another set, then that is known as a subset. So let's take a look. A is equals to 1, 2, 3, and B is equals to 1, 2, 3, 4, 5. Then we see that all the elements of set A are contained in set B. So we said that A is a subset of B. Yeah. Simply it means A is contained within B. Okay, so using this thing, we can, I'll clean this thing up and I'll write that, use this for our numbers, set of numbers. So set of natural number N is a subset of Z. You can see that it's contained there. And Z is a subset of Q. Every integer is a rational number as well, because suppose you got integer 2, it is nothing but 2 over 1. So that makes it a rational number. This is a integer, and that is a rational number. So Z, which is a subset of Q, which is a subset of R, which is a subset of C. So it's a important relation between them. Last, one more thing before we go any further is to talk about parts of these sets. So Z is a set of integers. If I do Z plus, it's a set of positive integers. And I do Z minus, it's a set of negative integers. And likewise we have Q plus, Q minus, R plus, and R minus. Just remember that when you do plus and minus, the 0 is not included. So 0 falls neither in Z plus nor in Z minus. Likewise here, 0 does not fall here and here. Now, having said that, I should point out one more thing. If you look at this Setbuilder form of rational numbers, you see there is a problem here. It's not complete. It would be complete when you say B is not equal to 0. Very important thing you need to also mention here. I won't explain this, but I think you understand what I'm talking about here. When we do that, whenever we're dividing by something, we always need to mention this particular thing. Okay, let's next we are coming to, we'll talk about intervals. So we have rational numbers, real numbers, and real numbers can always be represented on a number line. So we got this number line. Suppose this is a number line going there, and you have this value and you have this value, and your real, you can have all the real values between these two numbers. So this is suppose 2 and that is 4. Then the set, you can also show this interval using brackets. So this set here is, I'll write that as interval 2, 4. When you have square bracket, it means these two AND values are also included in the set. So there are billions of infinite number of values between these two numbers, and all of them are included here in this set, and that is inclusive of 2 and 4. If you want to write this, I can write this like this: x such that x is less this and that 4, and I need to say that x is a real number. Now here I want to make it clear that if you don't describe this, then it is assumed to be real number. So you can write like this, or you can write like this as well. Sorry, this is 2x 4. You write like that, that is enough, because it is assumed that it is a real number. If you don't want to include the end value, so look at this real number. I'll write that, I'll show this here, and this is solid dot here, and that dot is a circle. So again 2, 4. When the dot is solid, it is included in the set. If it is hollow, it is like a circle, then it is not. So this interval, and for this you normally use this small bracket. So this interval is 2, 4, but you want to include the 4, so you use the square bracket. And this set, if you want to write, this is equals to x 2 equal to 4, and you don't need to mention that x is a member of R, although many times I prefer to do it as a matter of habit. I normally write these things, write the set definition as well, write this domain as well as to what is the set in which x falls. So if you got, okay, let's take one more example. Suppose I got this value here, and that is also both of them are circles, empty circles, not solid dots. Then this interval will be 2, 4. When you use this kind of bracket, it means that end values are not included. And in set notation, you can write that this 2 less than equal to x, no, less than 2 less than x less than 4. And again, you don't need to write, but normally I write it like this, and you got that. Another example, let's take this, and this time these are the values that I included in the set. I didn't show this, but here I'm showing my set like this. This is the value 2. What it means is that I'm looking at all the real numbers greater than 2, not equal to 2. So this set will be 2 up to infinity, and I cannot use a square bracket here, because square bracket means you include the infinity. So I use this, and in terms of interval, in terms of set builder notation, I'll write like this. Now I don't need to write this, I just need to say that it's greater than 2, and then I say it is x is a member of R, it belongs to R. Just one more thing about calling them. This interval is known as closed interval, because you got square brackets there, and this interval is, these two intervals are known as open intervals. So these are closed intervals and these are open intervals. That one is also open because you got both these kind of small brackets here. But this is a mixed one. On one end, on this end it's a closed interval, and on this end it's an open interval. So you can do that as well. You can mix and match. You can mix them. Okay, so one exercise I want you to do. So this here. Just one more thing before we go there. But you can use this interval notation by using the different kind of brackets only for real numbers, because they are meant for real numbers. They are not for natural numbers or any other kind of numbers. Be very careful. If you want to give a interval of natural numbers, then you will need to use the proper set builder notation. You cannot use these. Okay, before we finish, I want you to give these exercises a go, and I don't think you would have any trouble here, so I will stop here. Okay, another thing that we need with these intervals is operations, very important operations that we normally do with sets. and they are known as unions and intersection. So let's go back to here. This is the previous section, and let's see what we have here. So there you go. So union is when you add the two. Union is when you combine two sets, not exactly add, and you combine in such a manner that in the resultant combination no two elements should repeat. Okay, so let's give it a go. Let's look at A. So A is this set 1, 2, 3, and B is a set which is 3, 4, 5. Then A intersection B, and that's the notation for intersection. A intersection B is you combine the two sets, but there's a 3 here, there's a 3 here as well, but we only write it once. That's A intersection B, A union B. And other one is intersection. Now in intersection we take only the elements which are common between the two. So in the previous case here, if we do intersection, this is the symbol for intersection. A intersection B is 3. Yeah. Just one more example. Suppose A is equals to 1, 2, 3, 4, and B is equals to 3, 4, 5. That implies that A intersection B is equal to 3 and 4. Yeah, if there is nothing common between the two sets, like A, suppose A is equals to 1, 2, 3, and B is equals to 4, 5, 6, then A intersection B is equal to an empty set. We call it an empty set, or it's also indicated as that symbol, which is 5, which stands for this. So where to use the unions and intersection? I can give you an example here. So suppose I'm looking for these values. So this is my, suppose this is 2, and I want all these value right to the end, and this is, sorry, this is my 4, and I want all these values here to the right end. Now this you cannot say, you cannot define this kind of set with any interval here. So what we do is we define two sets. One set is this, and other set is this, and then we do an intersection of these two sets. So we can do that using intervals. So in interval notation, I got a solid there. So basically it is minus infinity to 2 with a solid bracket, because the 2 is included on this side. Intersection, that's 4, that's infinite, and square these kind of smaller brackets on both sides, because neither 4 nor infinity is included. And if you want to do that using Setbuilder notation, let's give it a go. So this is a set which consists of X such that X is less than equal to 2. You put this, and then you put intersection X is greater than 4, and X is a real number. Okay, that's where we'll stop today.